Apologies for the good. So, last lecture I looked at this one example of integrated function system, and we saw that we could kind of solve the problem completely. We need to understood many aspects of it, and there's some reasons why this was such an easy system. It's not so easy in sense it's trivial, but actually the main feature there is that we have contractions all the time. So as we have contractions, and even if you apply them in a random way, you get rather predictable behavior. So in this lecture, I'll look at another example of random circle maps, and I'll introduce them. And then you'll see that these random circle maps are not contractions. And the question like, what can we say if we have a random composition of maps that are not just contractions? But in some sense, what we did yesterday can be extended to contraction. The first what I wanted to do is to just recap, after thanking again the one person for his help, is to just recap the setting of dynamical systems as we saw it yesterday. Let me just go over this. This is a little bit more abstract, but hopefully we can remember from yesterday what we've seen, and I'll just kind of hint a few things. So what happens throughout the lectures is that the same objects keep appearing, and I think it's important that you get familiar with them. So in some sense, by doing the different examples, hopefully we at some point get the picture of what we have here. So the theory was developed to a large extent by Ludwig Arnold and Paul Workers, and he wrote this book which I mentioned before. So the book has a lot of the ingredients, and another important person in the field is Poincaré in the back. And so they have various papers to elaborate on these kind of structures and consequences. So, as we call on the base, we have some kind of base dynamics for a random analytical system, and that basically models the randomness. So we have a probability space, the sigma algebra, and the measure, and then we have a natural action of this measure. This is basically how the randomness is generated by the omegas, and then we have a invariance, and we ask that the invariance is such that it's ergodic. And so we have an ergodic base flow, and that's the model for the noise in the dynamical system. As you see here, I described a little bit more abstract. So of course, yesterday we had very specific example here where we knew exactly how to do these simple sequences and so on. But it could be more general. And we see today an example where these things are slightly more general. But we always have such a base flow modeling, basically the noise. And then on top of that, we build the co-cycle. So we assume that we always deal with a compact metric space. Just to make life easier, tomorrow we'll have to look where we don't really necessarily have compact space. And for compact metric, of course, we like to have these converging there. And I make a kind of co-cycle. So we have the co-cycle space of E, and it has a part in the fiber and a part which is basically the randomness. And then we have the composition of phi from this co-cycle in the following natural way. And so what is important always that if we compose, that we always have to kind of shift the time variable in the right way. Okay, so then let me just remind you, sometimes we use different notations. I apologize for the advance. Sometimes I like to kind of think of the dynamic system acting on the space X. I like to write it like this, but if you're a bit more general, you like something like that. Just another notation. Okay, so then we are interested in probabilistic descriptions that usually satisfy in the form of invariant measures, and hopefully ergodic invariant measures, in such a way that it's invariant under the two-product flow. We saw that yesterday as well. Our mu was yesterday also invariant, and I also like that the marginal with respect to omega is p, so that I don't deal with some kind of like very strange realizations of my noise process. That's the model. Okay, so now, today we're also going to look particularly where we have some kind of parameterizable randomness. And so it could be, for instance, that our randomness, yesterday we had that in some sense. We had zeros and ones, we had coin tossing, right? And so, but it could be more general. We could have another way of parameterizing my dynamics with kind of a set of parameters. There's of course not a general way in which noise would arise, but it's a very natural way. So suppose that we have a set of transformations f alpha, where now alpha will be from some kind of set delta, and now we draw alpha's IID, the probability measure psi, from this set delta. And so this is some kind of, so for instance, this could be some math parameters in it, and the parameter can vary. I take it from the set. So yesterday we basically had a finite set, that's 0 and 1. And today we look at examples where this set is a little bit larger in a very natural way. And then we have some kind of structure, so I don't want to elaborate too much on it, but of course the space, the space of events now is some kind of like delta to the z, because in every moment in time, so the z will be the time variable, I have some copy of delta from which I could choose my realization of the parameter alpha. Yesterday it was 0, 1. I had 0, 1 to the power of z, basically these bi-extent sequences of 0 and 1. And then I have a natural shift action. It's basically kind of like look at all these events and these things, and I just shift them one place further. I always work with double time, bi-infinite time. And I have a product measure, so I take a measure in each of the set and I just basically multiply them if I specify the things in natural sigma multiplies at the Borel sigma multiply on this delta parallelogram to the power z, and we have this kind of invariance in a natural way just by the shift action. And so yesterday also we set up these things with the cylinder set, and so we can do the same, exactly the same thing here. Okay, so in that sense we have this kind of random dynamical system written in this form, in skew forward with kind of different properties. And now here explicitly this map phi is just f omega. And so we also saw that yesterday. And so today again we look at an example where this can be written in this way. And so this is slightly more specific than this general formalism. Just here I don't really specify where this noise necessarily comes from. And tomorrow we'll look at the stochastic differential equation, and then it will be not exactly the same thing. It will be slightly more general. So this is a special case, but it's a very natural case, and so we deal with this. Good. Then I just recall what we said also yesterday here. That you have invariance of probability measure. U for measurable dynamical system is called ergodic. If you have it has 0 or full measure, it's important result that you have this ergodic theory that says that if I take averages of time events, and so here I follow time orbit, and I take average, I take an observable and I average this, then this is the same as for the ergodic measure, taking the average with respect to that measure. And that's an important result that we often use. Okay. So then we have also kind of introduced these Markov operators. So we, as a standing assumption, we have to assume that the randomness is memoryless. So it's like picking the parameters IID, which is important. And so we can model the one-point dynamics of the random system then as a Markov process. I also did this yesterday. And so let this be the P of XU, you know, the initial probability to go from the point X into U by the dynamics in one time step. I can write this for the specific class of systems that I just indicated before. The chance to go from X to U is the measure of all alpha in delta, such that f of alpha of X will be in U. Specific, so this is a bit more an abstract formulation, but for the class of systems we just looked at, this percentage is the measure. And so yesterday, this was just always a half, or 0. Because the probability on each of these kind of elements, 0 and 1 was a half. And you just then we have this Markov operator, and what does it do? The Markov operator basically integrates, pushes forward the measure with respect to these kind of conditional probabilities. So it's like how the measure can evolve if I push it forward at the time as a stochastic process. So where all the possibilities, I carry all the probabilities, I take a probability distribution and I carry all the probabilities forward for the 1.1. Okay, now I can work this out. So I describe the evolution of the measure on the stochastic process, and I just here have the formula. I just insert here. So P of XU is this description, and I fill this in, and now I'm going to basically reading out what this means. Well, this thing I can replace by a d psi alpha and say that actually this is a characteristic function. Basically saying that alpha, I choose all alphas in X such that f alpha of X is in U. Precisely was this challenge here. So we applied it in a slightly different way. And then integrate also of the delta. So this actually gives you back this measure. But I can push it in the other way around now. I can use this characteristic function to resolve the end on the measure here. So I take these things together, and then I get precisely here that I leave the d psi. And I get this measure nu, and here get f alpha inverse. So that's precisely also what we saw yesterday. Yesterday I did a derivative, but I said that we have the Markov operator, which could be written as about the chance of something happening times the measure, the action of the map on the measure, which is the measure in the inverse map acting on the argument of the measure. And here precisely this is the integral of the delta with respect to this measure psi, that is basically indicating the probability that alpha happens, and then the probability is combined with the measure and the action of f on this measure, which acts on as the inverse of the argument. In the finite case, if we have a finite number of elements here, this is just a sum over pi times mu fi inverse of u. So this is my Markov operator. This is the way measures get put forward. But again, let me emphasize it. This is not the dynamics of the system. This is the dynamics of the Markov process that you induce. But this is not actually describing orbits of the system. This is just a probabilistic, stochastic process point of view where you think of like what happens if I had a distribution of particles like an parallel universes with different realizations of noise, and how could this then solve forward if I didn't know anything. And so these things are very different, and it's important. If there's only one thing that you remember of this lecture, hopefully it was that actually there's different points of view. You either look at the dynamics of given random events and how the dynamics evolves. And so if I look at more events, then I also all of them I want to have the same noise, basically. Or you say, like, look, I have a parallel universes approach where every universe has its own realization of the noise. And I just don't know what the realization of the noise is, so I just take them all together and it just tells me something. So the Markov operator approach is basically parallel universes. I take all these things and I just let all possible noise run. But it doesn't tell me actually something about the dynamical process of the system that you experience where there's one noise. It's a kind of important difference, and I think often it's because this approach is much more common than the other approach. People usually think that this is just an approach to do, and someone must know why we do this. Right? I think it's important. But of course, it's not it's also a useful approach for some questions, but you just have to understand which technique to use and to which question it applies. Okay, so stationary measure. A probability measure is stationary if it's invariant over a Markov operator. So that's we saw that also yesterday. We found a very natural measure on this Cantor set, just a stationary measure. So in general, we can have many, we can have more stationary measures, and such measures will be in the compact space. Will be non-empty. Will be closed. Will be convex. You can take positive. You can add measures together, but not, with negative measures don't mean anything, so I can only add in a column, so I get this compact set of ergodic measures in general. And then the ergodic, and that's of stationary measures. The ergodic stationary measures then are the extremal points of such compact sets. Okay, but I don't really go into that. Good. So let's look at this this closed cycle. So if rho is a stationary measure, if a product measure is invariant, that's the same. So if I take actually this thing and then I take the product, this is the all realizations of the noise together, then that's also the flow invariant. And we call it the thing ergodic if this measure is ergodic for the flow. So this is basically restricted. This is the measure that sits only in the phase space X. This sits on the Q product. And so ergodicity here basically implies some kind of ergodicity there. And you see from yesterday why this happens, because we apply Vehicles ergodic theorem, which it basically doesn't really does anything about this kind of measure, because we need some kind of dynamics. But if I apply it to this one, then I never naturally get the measure rho out of the end. And so we call stationary measure also ergodic, even though it doesn't have the same dynamical interpretation as this measure has for Q product. This is the right one to use, and this is the one you end up with. Okay, so then we have this integration of invariant measure, and so we saw that yesterday. So let me just recall that, because it's kind of important, because then we get this kind of so-called Markov measures out. So if we have a probability measure mu for the Q product, which is invariant, so here psi theta t star mu is mu, and I have the right marginal, that goes in invariant measure for the random dynamical system. And what I can do then is I like to kind of like pull off this measure on this omega fiber somehow, right? On these omega constant fibers. So how do we do that? Well, this general procedure is just a general analysis procedure. There's nothing special about it. So I can basically write this mu a out in this following way. So this is a characteristic function over the set A in the x omega space as a full Q product. So P is the marginal here that's given, and what I then look at the disintegration in this way. And if I write it, then this will be precisely this mu omega defined. It will be defined in this way by the set A omega, acting on the set A omega, where A omega is precisely the part of A that slice the section of A at omega. And so if A is a big set, I have my omega space in the bottom, I pick the omega and just loop up, and I cut through A. And of course, this naturally this A sits down in space X, in the phase space. And so the important sense somehow is to see that indeed this set is slow invariant in this following way. So if I apply the dynamics to mu omega, I precisely end up with the mu theta t omega. So just shifting the time. Okay, some properties. Some technical properties I think maybe good to walk through, but we have proved them. So for P, almost all omega, the map from the U to mu omega u is a probability measure. That means we have basically probability measure on these A omegas, on these slices. And for all u, the map from omega to mu omega is as measurable as the sigma algebra with respect to this measurable map. And technically speaking, we used to talk about random measure in this sense. But this map from omega to mu omega is, sorry, it should be u here. If this map is measurable, so like usually we want everything to be measurable, otherwise we don't really know what to do with it. So this is a random measure. This is also satisfied. P almost all omega. Do I repeat this? Oh, sorry. Repeat this. It's the same statement here. And it's a Markov measure. And so for the Markov measure, I said before, if the map of omega to the probability measures is if it's measurable with respect to the sigma algebra of the past. And this always looks a bit cryptic. So it's now a sigma algebra of the past. And look here, this is a sigma algebra generated by the sets omega to omega n minus infinity. So it says the loop on the back. And so in the previous example, these were precisely basically my subsets of the Cantor set that I identified. Because I knew that my mu omega, which was a random fixed point, was measurable basically in terms of those sequences from the past. Right. So this is a subset of the events in the time. But the important thing is that somehow to measure the mu omegas, I only needed the past. So this looks very abstract, but I think this is maybe somewhat difficult to digest. But if you think about what happened yesterday, we know what happened because we had simple sequences. And then we know that actually the mu omega just depended on the omega minus 1 to omega minus infinity. And of course, that's measurable with respect to what? Well, with respect to the way how we measure the time events from the past. That's basically what it means. So if you look at the Google Bluetooth Einhold, you get constantly set statements flying around. But maybe it's good to have an easy fix. I hope that the example that I gave yesterday, these very abstract ideas have some kind of concrete idea. Of course, in different contexts, they look slightly different, but in this specific context, it's all very concrete. Okay, now Markov measure versus stationary measure. So we have this stationary measure and the Markov measure, and I'd like to kind of say something about how they relate to each other. Because they're two different points of view, but they're kind of related to each other. Right? So yesterday, of course, I spent most of the time, again, in this example, illustrating that, but let me now just basically spell it out more explicitly. So the stationary measure, rho was the empiric measure, and with respect to a Markov measure, we can define rho as the marginal with respect to the phase space x of this measure. And so if you take the marginal of mu with respect to the time variable, or the noise, I get p. And if I take the marginal with respect to x, I get the stationary measure. Okay, so what is this marginal? This is precisely this guy. Right? So the rho of u is defined basically as the mu of u cross omega. And this is this guy. Okay, let's now here check that this works. Okay, let's check that this measure is indeed stationary. Okay, now what we do is we really make a separation of the time in past and future. And it just helps us to basically understand this formula. So I just write the space like this, and I think of this in symbols as like basically we have the dot, and the dot separates the future from the past. So I write omega minus, that's the past, and omega plus is the future. Right, so omega minus is all the sequence from omega minus 1, omega minus 2 to the back, and omega plus is omega 0, omega 1 to the front. So some objects that we deal with, they are measurable with respect to the future, and some are measurable with respect to the past, and it is handy to separate it. So to show that it's a stationary measure, we need to show that this rho is invariant. So that basically is invariant with respect to the Markov operator. So I integrate over omega, and I'll affect the flow invariance on the measure. so now we have to kind of look at what this thing is, and now we just observe that the inverse of this map actually only depends on the future. Doesn't depend on the past at all. Take the omega, we always look at the omega 0 and from forward. It doesn't look at the back. So this integral actually is just the integral over omega plus. There's nothing coming from the other side. And so this is this item, and now we can just basically work it out. Divide this thing out, and now just I insert the expression for a row that I had before, which is integral over this one. Okay. But now this one, here's the mu omegas, and the mu omegas, this guy only depends on the past. Right? So actually I can, here, when I take this integral of the mu omegas, I can basically restrict just to the from the past. Because this mu omega just depends on the past. So I have the integral here over the argument here is an omega plus, and the argument here, the other omegas is just over the past. And then I work these things out. Okay, and if you now look here, here's the mu omega of, and this operator, this is the time operator. I know what it does on the thing, it just shifts the time. It shifts the time. And the integral of the whole thing together is just omega minus omega plus the whole value. And this is precisely what I wanted when I wrote it 2 times the same line. Yeah? So what I check here is that indeed the row is stationary, which is the invariant of this procedure. Okay, it's vice versa. If row is a stationary measure, then this object is an invariant Markov measure. So this is the associated disintegration. Okay, so it's important that it does depend on the past, and we can check the invariant, but it is yesterday as well, in a specific example, so that this guy acts on this guy. You act this in here, then we get here the action of this thing here, the action. But what happens is that this other new element just kind of adds the sequence of transformation that I have in here. So what happens, you get precisely this, you get one shifted in the sequence, and the shift precisely comes up over here. And so when yesterday I did it with the T, I had the T omega on this thing, you see the product evolving here, and then what you have is just get an extra one inserted here at the end. And this will get you just basically one shift in this process. And so indeed, we have the right invariance that this leads to the time shifts in the argument. Okay, good. So what I didn't do now, I spent good 20 minutes now just basically going through an abstract framework which is really essential for this thing. So everything that I said here, basically, I said yesterday as well. I tried to make it more appetizing by just having a very concrete example. So I think one of the obstacles of really coming to grips with all these things here that we have some different concepts, and one has to kind of be careful to kind of keep the concepts out of each other. You have a stationary measure, Markov measure, you have different points of view, you have kind of rather abstract setup. And that makes it a little bit sometimes difficult to access, at least in my experience, to what actually is going on. So if you open the Arnold book, that's precisely the kind of thing that you will run into, is that there's a lot of things there and very interesting things, but the question is like, what does it really all mean if you're not really familiar with all the notations? I often talk to people that are very interested in random mathematical systems, and they try to read the book, and they say they find it very difficult to get into it. And the problem is that the language is entirely appropriate, but it's also at an abstraction level that for many people it's difficult to get into. Anyway, so what I did here, so these slides basically are more in what you would kind of expect in the literature to see on this kind of statement. But I hope that with what we did yesterday, that we can see that this is not something to be scared about. It's just a matter of that we should embrace it and think of simple examples to be confident that, of course, these things should be true. And of course, there are variations of this truth in different contexts. And yesterday, I just presented a very natural and simple one. So I hope that that comes across. So it's very useful actually to look at these kind of things and go back to yesterday's lecture to really do the one-to-one correspondence. So I tried here to kind of like, I hope you remember something of yesterday that's still with you. That you see that at least I'm talking here about things that are natural. Yesterday I often showed just for the specific calculation, I just calculated that one thing is the same as another thing, just for the example. But here you can see that actually in some generality you can do some general setup where actually these things are in general correct. I didn't really specify anything about yesterday's example here, I just basically did it in a more abstract way. So the truths that I said yesterday for the example hold more generally, and specifically they also hold for the example that we'll talk about today. Okay, good. So to kind of walk back into yesterday a little bit, yesterday we did iterate a function system with contractions, and this was kind of very easy to manage. And I'd just like to kind of summarize two properties that we saw already yesterday, but I think they will be useful today as well, as we shall see. So the first is that if you have a random dynamical system on a complex phase space that consists of the random iteration of contractions on the space, and in such a way that they have a uniform contraction rate. It means that it's not that they're weaker and weaker and weaker and weaker until no contraction. We have a certain bound away from 1 as a Leibniz constant. Then it has a unique globally attracting random fixed-point vector. Not so surprising, because what we do, we just going to multiply, we compose contractions all the time, the uniform contraction rate, and no surprise that by contraction principle, somehow for the pullback effect will get isolated. So we have indeed this. And for instance, an example, take xn plus 1 is 1/3 times xn plus omega, where omega is a random variable between, O minus 1, but omega is a random variable in the interval minus a third. Then all our orbits eventually converge to the region A is 2/3 and a third. So we get here some region where the orbits kind of so what you have is that the points come together in a smaller set. So you start with -1, -1. It kind of goes outside, but then of course it can basically add up to something. But it will. Is it right that it is? There's a bounded subset. I'm a bit worried that maybe this numbers are not correct. But this is clear that you contract from -1 to a third, and you can mostly apply, go 1/3 higher, and then of course you attract again, and so on and so on. So you get a kind of compact set where you go to. This point is in fact it will be random because you can always kind of always have an extra omega, which is in minus a third. It can go anywhere, but it will not kind of go outside. It's a random fixed point vector because all points get affected. Yeah, I think this number is not entirely correct. It's a good exercise to compute the right number. Yeah. So what's the right set? Okay, and also with the random composition of contractions, we have of course this result of the uniqueness of the measure using the Hutchinson metric. We saw that contracted random dynamical system gave a contraction for the Markov operator, so we get a unique stationary probability measure. So I saw all that yesterday we did that. At least I didn't really depend on this result. So if you have just contractions, then you have a simple situation, but you also have random fixed point, and we have unique stationary probability measure. Good. But the topic of this lecture somehow was supposed to be circle homeomorphism. So we'll go now to the circle homeomorphisms. As I said, but I wanted to really kind of go over this general theory a little bit because, and maybe tomorrow we see another realization of this, and to just make sure to reiterate that we know what this is about. So we will see now kind of how this whole structure that I just described, as you also saw yesterday, then also applies to this case. So circle homomorphisms are very well-known examples of dynamical systems. So here we have a circle, and so circle homomorphism is just a map of the circle to itself, which is invertible and continuous. And so the question has been kind of like, well, what kind of dynamics can you have of maps that map the circle to itself? So this is one of the most elementary questions in dynamics, being very well studied, together maybe with also transformations of the interval as a one-dimensional dynamical system, just a map on the circle to itself, and you ask like what kind of structure. So this is very well studied. So one way to model this is to kind of use complex numbers, this is kind of like angle value per set. So think of the circle as this object. And let's just confine ourselves to the orientation preserving homomorphism, so means that if I have 2 points that they keep the same orientation on the circle, so we don't allow for reflections. No reflections allowed. And so what happens is, because of continuity, what happens is things are just basically rotating, but they're not uniformly rotating. That's basically what happens with the circle homeomorphism. Because you maintain the ordering on the circle. Okay. So most importantly, if I have a circle homeomorphism and if it's contracting somewhere, then it must be expanding somewhere else. It's impossible for a invertible map to kind of just only contract and not have some region where it also expands. So we definitely, for circle homomorphism, we're not in a good shape to use our random contraction type of arguments, because I will know that for my circle homomorphism, I will have to deal properly, in some sense, with the fact that they are not contractions. And so that's maybe the first statement here. The circle homomorphisms are not contractions. So the question, of course, then, what can we say about such things? So of course, what we want to build up to is to make some kind of random model with circle homomorphisms. And with just some history, how do you look at this circle homomorphism? Usually we take a lift, we go from the circle to the line R, but then everything that we do is not one. So we identify the line, which is a covering space, then back to the circle. And so if you write down the equation of motion of such a circle map, we usually do it on R, because it has natural coordinates there, but we have to make sure that everything is taken mod 1. And of course also the equation has to be equivariant with the shift of length 1. So if we shift of length 1, we get the same with the equation of motion out, otherwise it would be inconsistent with the lift. And the rotation number is then defined as this thing. What you do is you look in the lift, given the lift, you look at the lift and you just measure how far you move after an iterate, and you divide it by n, so you get the average excursion you take. And this gives you some kind of number. It will sit sort of between 0 and 1. Okay. Of course, you take it mod 1. If you take it mod 1 to get rid of the choice of the list, you can take different choices, and if you don't take mod 1, you get just artificially different numbers. Good. So why is the rotation number important? Because of Poincaré, who has shown that you can explicitly classify the behavior of this circle homeomorphism in terms of rotation number. So, first of all, the rotation number is well defined, it's independent of the lift, and it says something about the dynamics. So if my rotation number is rational, then I know that my map, or my circle map, has a periodic orbit. And actually, and also the other way around. If it has a periodic orbit, then the rotation number is important. The rotation number doesn't depend on the initial condition. So you have the definition, the initial condition. The importance is the rotation number does not depend on the initial condition. It's easy to see somehow because we have this. It's like a train, right? So and everyone sits in line, and you cannot really overtake. So if someone goes around at a certain speed, everyone is forced to go around at the same speed. So in circle maps, rotation number really is a very good characterization of how fast the dynamics goes. And it's impossible for different points to go different speeds because then one should overtake another one. And because we have homeomorphisms, it's impossible. We transfer the circle into itself, but only in an invertible way. And it means that everyone sticks behind each other. It's basically a train on the circle. Good. Right, so we have this relation, and then if it's irrational, we have semi-conjugacy to an irrational rotation. And it's semi-conjugacy because there's some technical problems, but if it's smooth enough, it's C2, then we know it's actually conjugacy. That means you can actually find a coordinate transformation if you map it into irrational rotation. So in irrational rotation, that means that everything rotates with the same speed, apart from coordinate transformation. In the rational case, we don't really have this conjugacy to rotation, typically. But what happens typically is that we have a periodic orbit, say of 4 points, period 4 orbit, for instance, that points are mapped around. And then what happens is we have some of these orbits will be stable, periodic orbits, but there will have to be other orbits in between that are unstable. So we get like some kind of a pair where we have a stable and an unstable orbit accompanying each other, and everything in the middle just basically kind of converges to stable orbits apart from the unstable orbit. And that's a typical behavior. We can of course have multiples of such things. We don't know exactly how many periodic orbits we have in general. But if we have a rational rotation number, then we have a periodic orbit, and then typically this periodic orbit will be isolated just by general hyperbolicity argument. And if you have such an isolated orbit, we have an accompanying orbit from a stable and also unstable orbits, and we have multiple pairs of them.
To be honest, the last line is one of R is F.
Sorry?
It's a conjugacy between the original F and the rotating.
Yeah, oh sure, this is of course
so what R is?
Point F, yeah. Sorry, this is
one is
this is F, yeah, sorry. Yeah, one of them. That's right, this R is H here. Sorry. Yeah, so the whole picture is that we have kind of rather complicated but very well understood dynamics. So why do I take this example? Because it is an example which is very well understood. Maybe the previous example was a contraction, and for contraction, like x goes to 1/3 of x. So in the previous lecture, everything goes to a fixed point. So that's so boring. But now this is much more difficult, but it's also very well understood. And so it's a typical thing that happens in dynamical systems course where you can actually prove all these things relatively straightforwardly. So let's look at an example, and I think there's also this well-known example of Vladimir Arnold. And this is the Arnold family. So we have xn plus 1 is xn plus omega minus some k divided by 2 pi sine of 2 pi xn. So this has to be periodic function because we have that commuting the shift of 1. And I take this mod 1 to kind of wrap it back on the circle. This is just on R, and mod 1 to put it back on the circle. And so omega and k are two parameters. So if k is 0, then it's just a rotation. And omega would be the rotation number. Because everything just shifts with a certain speed. So the omega of the rotation number at k is 0. But then you have just linear rotation, which is boring. But if k goes non-zero, then it becomes more interesting. K cannot be too large, because then it will not be invertible anymore. So I have to put some bounds on k. So it's here k is 1, precisely on the boundary. And yeah, so we have this kind of two parameters. One is non-linearity, basically steering away from the uniform rotation, and omega is basically setting some kind of base on the speed of rotation, even though it's a non-linear rotation. Okay, so now famously, this map shows the mode blocking. Here you see a certain numerical experiment of what happens. So if you, here's omega, so this rotation speed, here's k non-linearity. So if you look at this diagram, that is okay. This is at k equals 1. This is rotation number rho. Sorry, this is rotation number rho at k equals 1, and I vary omega. So k is 1 means I have a strong non-linearity. And so what happens if I switch on omega, and for a long time it stays 0, and then it starts growing. But you see very clearly that there's a lot of plateaus. There's a lot of regions, like here, where the omega is constant. That's what people call mode blocking. And so mode blocking is a process that is really studied by the circle map. So the original model somehow is actually more as a time one map or a return map of a process on S1 plus S1. So think of a time varying process, maybe an oscillator with an angular variable which is driven by a time periodic process, and then I can ask how do I study that? Well, what I do is I take the Poincaré section here and I look at the return map. The return map will be some kind of homomorphism or diffeomorphism, and so that I get rid of the time basically by looking at discrete time as a return map, and then if I have a periodic orbit here, what it means is that my oscillator will resonate in frequency with the driving of the system. And so this mode blocking is the fact that we see that often in applications when you drive something with a periodic signal, you get a response signal which is resonant with the driving signal. And so in some sense this phenomenon is well demonstrated in this circle map, where we see precisely that there's a tendency in these plateaus, there's actually very many of such plateaus, of the system to get locked into a frequency which is equal to the driving frequency noise. But it's actually a bit more pronounced. So it likes to stay in some frequencies more than in others. So a different picture here is with Arnold terms. So here I plot omega versus k. That comes from some book. And so the rotation number here is given in this region. So that might be a bit difficult to read, but here's 1/2, here's 0, it's a third, fifth, fourth, etc. So we look here in space omega versus k, and I look if I switch. So here we have basically all the rotation numbers sitting equally because it's just basically there's no driving. And if I switch on the driving, my region with 0 rotation number grows linearly, and other regions also grow, and it gives this kind of complicated picture. And so the question, your famous question was like, what is precisely the set of omega values for which you have rational or irrational rotation number? And that's these are kind of complicated questions. So what I wanted to show is that we have some kind of like insight here. We have this regime where we have most of the time periodic, actually most of the time we have periodic plateaus everywhere, and then sometimes we have irrational rotations in between. And all these things are very well understood. But we also have this dichotomy between attracting and expanding behavior. So in this periodic region we have the contracting and expanding behaviors going together. Okay, maybe it's a good time to have a quick break, and then I start talking about the random version of this Arnold map and see what the dynamics is. Maybe 5 minutes or so. Okay. Okay. So what did I do in the last hour? I basically went over abstract random persistent framework, and then I introduce circle homomorphism, so there's nothing random in there yet. So now I'm going to look at random circle homomorphism of a special type. Just look at an example like yesterday. So we start with the diagonal circle map with some parameters that I choose. K is 1, that means like strong nonlinearity, and omega is a half. So what does that mean? It means that rotation number is a half. And you saw maybe, if you remember from the graph, we have this theory of a half. You see there's a wedge coming out with a rotation number a half. It's a pretty strong resonance. So when I choose omega as a half, straight above it, yeah, I'm pretty sure that I have rotation number a half. And indeed, I have an effective period of 2 orbit, and it's just one of them, and you see here the graph of the function of f squared. So what is the graph here? It says that x against f of x, and you've seen these things, and so on the diagonal we have x equals f of x, it means a fixed point. So if you look at this graph, I can basically read out that there's 1, 2, 3, 4 fixed points. Now, 2 of those fixed points are repelling, and 2 of them are contracting. So how can you see that? You look at the derivative. So here the derivative is larger than 1 for the graph. That means that the map is expanding, hopefully. So this is a repelling fixed point. Here the graph has derivative smaller than 1. It's contracting, it's repelling, and this point, these are equal to each other. Because it's on the, so you have 0, 1, this is the model of the circle, so think of it as being wrapped around. This point is identified with this point, and this point is also identified there. Right? So we have 2 attracting points, this point and this point are attracting, and 2 repelling points. So just precisely a bit like this, a simple, not period 4, but period 2. So we have a consecutive repelling and contracting region. Okay, now I'm going to randomize this in a certain way. I'm going to randomize frequency, omega. So I'll take omega to let it be a half plus alpha, where alpha will be randomly chosen at each iteration with uniform probability minus epsilon to epsilon for some epsilon. So I take some little variation, and I'll just shake up the map. Sorry, and here's the alpha. So the resulting map is f xn plus 1 is f alpha of xn, and we have this map, half plus alpha, so put the alpha here. So we just have a very concrete map, and we try to follow what's going on. Okay, so what is the abstract concept of this map compared to what I just said in the hour before? That we have this kind of basically have the noise space is basically interval minus epsilon to epsilon to the power z, because at each point we can choose such a noise level. We measure this by the product measure of the probability to measure here, and then the product here, so the size probability here, and then we take products, and we measure this with respect to the Borel signal algebra just on this closed interval. So we just measure on a certain interval here what probability is, and so the set of which we can measure things is precisely this set. And then we have the sequence space where we just do the omega space, we come that out of this minus epsilon. Yesterday there were zeros and ones, now it's just numbers in minus epsilon. And in a natural way, you have this thing being invariant under the shift operator. Very natural way. There's a product. The product measure here doesn't really see differences. So every p measurable sigma invariant subset of omega has full p measure under this thing, and we have this sigma subset of c. That would be a little exercise. Anyway, so we have the kind of co-cycle, and the co-cycle here is that we have f of omega 0, that basically you read of the right symbol. What is a symbol? The symbol is a number between minus epsilon and epsilon. You put it in your snap. And this is what you do. Path of omega 0 is you read the symbol and then the number and you put it in your map. And then we shift the omega one form. So it's very, very concrete. And it looks hopefully a little bit more pleasant than the previous one. Okay, so now we examine the random map and the noise is small. Sorry, this is 0.02. There's a 2 here, not a 5. Because we actually did it first with 0.05, and then it turns out that it was too big. But we only found out later. Okay, so here you see a picture. Is that the right picture? So here we have. So what we see here is we have the following things. Let me maybe make a sketch on the circle here. So we have 0.5 being attracting points, and there's also some repelling points somewhere. I don't know where they are precisely. So what happens? I add this noise. So what do we expect? Well, typically, without the noise, everything just basically was attracted by the period 2 cycle. So the points jump back and forth here. And if I add some noise, then this will be becoming some fuzzy, because I'm here and then my noise kicks me a little bit away, but then my dynamics will pull me back in and so on and so on. So I get some kind of, it's not so unreasonable to see some kind of like noisy bit on both sides, where the points keep jumping back and forth between the two touches. So what's plotted here is precisely such an orbit. And so we plot an orbit, many points, but and you just plot, so you take a point and then you plot all the next points and they tend to be kind of just jumping back and forth. So there's a video that I have. Let me see if I can get that going. That would be nice. This one. So it's a repeated video. So where there's 2 points starting, so here you see this point going back and forth near the top. But it starts here, then it starts going somewhere, and you see what it's doing. So you see what it's doing, it's just kind of jumping back and forth. Right, so I put it in a loop because otherwise it's so short. Yeah, so this is basically what you see. So we get attracted to these regions, but we have some kind of erratic behavior around it. So this is also, of course, in line with what we saw, things we saw yesterday, for instance, in the Okay, so how can we analyze that? Well, I can analyze this by actually plotting. I just plotted the graph of the function, but I can also plot, I now plot basically the range of my map. So I have several maps, f alpha, and I'm plotting here the f for alpha minimum and f for alpha maximum. So the alpha minimum was minus 0.02 and the maximum was plus 0.02. And I plot them. So what do I see? So the red one is the minus 1, the minimal one, and the other one is the. So you see here that the difference between these graphs is not entirely uniform. It's because I took the 2 times iterate. And with the 2 times iterate, the noise comes in, the epsilon comes in a non-linear way. So in the beginning it was just shift by epsilon, but if I take the 1 iterate more, depending where it sits, because there was a sine function in there, so it gets a little bit mixed up. But it's nice to look at the 2 times iterate because there's a period 2 point. Then look at the 1 time iterate, it's a bit more difficult to analyze, just from the picture. So where does our motion is? Our motion is between this graph and this graph. Actually, there's a lot of other graphs just in between. This whole region here is foliated by graphs, f alpha, where alpha runs from minus 0.02 to plus 0.02. So my claim is that this graph is very useful to analyze the dynamic of this system. For instance, I can identify where my attracting set sit, if there's any set where points are attracted. And so here I do that by some lines. So what am I doing here? I look at sets which are invariant under all the maps. How do I do that? I look at the lower map and see where it has a fixed point, here. And I then look at the upper map where it has a fixed point, and the region in between that I captured, precisely those that also left invariant with all the maps in between, because they just map into the interior. And in some sense, the fixed point of the lower map and the fixed point of the higher value map, they act as stopping points for points to go anywhere. So any map that's in between here cannot really go past this point, it cannot push anything past this point, and any map that's above here cannot also push a point backwards. It's impossible. So this set here, is indicated here, it's invariant basically under all possible applications of F alpha, for all possible alpha. And I see also a region here, and of course they're part of this region that map back and forth by the map F alpha. So the combination of this region plus this region, these are connected, because it's just a circle. And this is 1 and 0 is the same point. So there's two intervals, and this set, the union of these two intervals is left invariant by all maps F alpha. So these maps into itself. So we have here this set is precisely what you basically see here, roughly. And what you also see from the dynamics is that actually all other trajectories will be attracted. If you just follow how they iterate through these things, they will be attracted by these regions. Okay, not such a big surprise, because if I take a small noise on something that I know that has a strong contraction principle, everything goes together. If you add some noise, everyone would expect to say, well, you add some noise, you get some noise, right? You get basically the same phenomena with a little bit of noise on top of it. And that's of course precisely what we see. The nice thing is here, so when I said we got the wrong numbers, when we plotted this graph for 0.05, we saw that this is actually not working, so we saw that we made a mistake. But this analysis is much more accurate than a numerical analysis actually, somehow, because you can, anyway, I can make a comment on that. And so if you compare this to this picture here, then these regions, you see also the regions not equal in size. And you see these regions here also not really equal. So these are regions very small, and these other regions are a bit larger. Okay, so we have here, this is a bit like the set E we saw before, right? Yesterday we had a set E, which is a Cantor set that attracted all orbits. And here I have a set that is two intervals, which attract all orbits. Okay, so we look at stationary measure. Numerically, so what do? I assume equidicity. I just calculate history, the histogram of an orbit, and I just ask, like, I make little boxes, and I ask how many times do I arrive in a certain box, and I plot a histogram of that. And so what you see, yes, we end up with a lot of points in the middle, a lot of points on the side, and nothing in the middle. And so we take a transient, maybe we take whatever 10 to the 6 iterations. And there's a certain number of beginning points that we just throw away. And so this is an attractor somehow with this kind of some density. Okay, can we theoretically understand what happens here? Is this under control? Yes, it's under control, and we know everything that we need to know. Why? My claim is that the attractor is actually a random fixed point. So UA is an invariant. UA is the set of these two intervals, right? Is an invariant set for the dynamical system. Why? Well, on UA, first it's attracted from point outside, you can see it from the graph. But on the set UA, all the F alphas are contractions. How can I see that they're contractions? I look at the derivative of the graph. The derivative above this is I can just visually inspect that the derivative of this graph here is smaller than 1. So there's only contractions.
Is it a random fixed point with respect to second iterative?
Yeah, well, it's for the second iterate, it's also for the first iterate.
For the first iteration.
Also is also true.
Okay, if you consider two together, but what if you pick only one and use?
So this region, of course, not invariant. We jump from here to here and backwards. I'm just analyzing the second iterate, but if it's true for the second iterate, it also holds for the first iterate. I cannot.
So can't you say random periodic orbit, random periodic orbit of period 2?
Something like that. Yeah. I'll get back to that formal idea tomorrow. Actually. But you can say something about this as a random periodic orbit of period 2, in some sense. Yeah. But of course, there is no periodic orbit. But there is some point jumping back and forth. Yeah. Yeah. So of course that is the idea. We had a periodic orbit. It was attractive. I had some noise. Why not random periodic orbit? So but the nice thing is that we can see this contraction because the graphs, like the graph here, is almost flat. It's definitely the derivative is smaller than 1. And it's here too. So I can basically see that. I can of course also prove that. I can go to the function, compute this, but you can see it here. It's contraction. And we know, so now we have a set which is a compact phase space. It just restricts to this invariant set. And I say now I have a dynamical system on this set, because everything got attracted with it. And then I have a set of random contractions. But I know everything about random contractions. Because we just said by contraction principle, we have a random fixed point. And by the Hutchinson kind of construction, we also have a unique stationary measure. But we get all these things just for free. We say the microprocess has a unique stationary measure, and the attractors and attracting random fixed point. So no mystery here, which is good, because we didn't do much. We just added a little bit of noise to something which looks extremely stable, and we get something out which is well understandable. So, but of course we're in a realm which is slightly different from yesterday, because yesterday I had only 2 maps, and now I have a whole bunch of them. And yesterday I had a Cantor set, and here I had 2 intervals, on which I contract. And so this looks a bit like, this noise looks like for some kind of noisy application somewhere. Maybe the application of 2 maps yesterday doesn't look so physically. It looks like something like noise. Okay. So what happens if I take larger noise? Well, if I take larger noise, I don't have any invariant subset anymore. So this is my graph of F2 for larger noise. And what you see is here that the regions here are now like this, in between here. Then it goes in there. You see there is actually no stopping points anymore. There's no intersections of this graph with the line. So what you see is that basically points can just freely move back and forth. So what does it mean for my system here? That basically the stationary measure will be spread all over the circle. Okay, so how does it happen? Well, there's some kind of bifurcation happening here, because I had this nice invariant set, and now I say, well, if I take a much larger noise, I have nothing anymore. So what happens in the middle? Well, here I try to kind of numerically find a value where precisely the transition appears. It's about 0.04. And you see here what happens, characterizes it when you have precisely the tangencies, the points that used to kind of intersect transversely, the 2 points, they kind of get detached from the curve. And you can see here the associated invariant sets. So what's important to note here, and I will come back to that on Thursday actually, is that I have these invariant sets, and they grow, and there's a certain point where they just disappear. Right? So it's not true that I have these 2 invariant sets here, and they grow and they grow and they grow and they grow until they hit each other, and then they're one circle. No, they grow until they can't grow anymore, and then they just basically explode. It's an explosion of the invariant set. Okay, and that's already at 0.04. So I have 0.2, I'm much beyond that. Much further. 0.1, I think. Maybe it's 0.1 actually, the picture. Sorry. I will correct this on the slide before they go. Okay, so the interesting thing is that if you now look at the numerics, then it seems to show that after the bifurcation, after we get this one invariant measure, that the trajectory synchronized. So if we look at the distance between two orbits of two different points, it looks to be that for different points, this distance between the two points goes to 0. So you cannot see this, but right, you can. But so let's have a look at this movie. Again, it's on a loop. So let's wait. Oh, here with 2 points. And then they start meeting each other and then they loop up together. And here we again have the 2 points, 2 different colors, and then they meet up. Can you see it? It goes a little bit fast. So let me here different points. No? And we have different points. I'm close to each other, and then I'm more on top of each other. That's not a proof, but it's so there's something interesting. So we have a random fixed point here. We can understand in this random fixed point here because we have contractions here. We have contractions here, contractions here. Right? Now my whole area breaks up. But now I have also I don't have contractions anymore. These circle homomorphisms are not contractions at all. Because they contract here and they expand here. There's a certain kind of game going on. It's like who's going to win? Are we more contracting or more expanding? So you can just do some kind of thoughts about this. So how would you think of this? Think of a stationary measure. Look at the stationary measure. And you have some areas where you expand and some areas where you contract. So somehow this video seems to imply that you spend more time in the areas where you contract than in the areas where you don't contract. For the stationary measure being everywhere, so you can't go everywhere. So you'll also go to regions where you repel, where you expand. But apparently you spend more time relatively where you contract than where you repel, because otherwise we wouldn't see points being contracted, because it looks like we see just contraction. But we know it can't be like that. And so this is not the argument. But there's a game going on somehow. It's a bit of a philosophical game. So, who's going to win? So it looks like the contractions are winning against the expansions.
Contraction is winning because it is a randomly perturbed critical circle mode, which has a strong stable the derivative 0 point. So the attracting fixed point has the derivative 0. So it's a super stable. How much that is?
Yeah, that's not so important. No. Yeah, you're right. Of course, you're right. We took k is 1, but you can also take any k. K is 1 is an extreme formula, but again, k is 0.1. Also okay. Also okay. Yeah, you're right. Of course, I get a very caricature picture because I push the circle map to the end. But you can do the experiments also. Yeah, of course, this does the action a little bit more fast. But Professor Kupu was right that he says that because we take k equals 1, our stable points are extremely stable. But actually, that not really does matter. No. Okay. Good. Right. So the question is like, how can we understand these behaviors? And so the question is like, can we sometimes measure the contractivity? So one way to measure contractivity is looking at the atomic exponent. So here's the atomic exponent, and then final two. So suppose we have an ergodic measure then we can look at the, we can try to use the ergodic theorem somehow to get some good expression of the average contracting rate along an orbit. So here I just define the thing along an orbit. So I take the derivative, I take the logarithm to get basically the exponential out of it, 1 over n, so this is the log of the n composition actually of these things, of the maps, so I take the derivative along an orbit, and I ask basically on average, how much is it expanding or contracting? And take a limit sub to make sure it exists. Hopefully the limit would exist, but if it doesn't exist, then a limit sub doesn't exist. So what does it mean actually? That means that I look at I measure the thing along this function f, but at the points kind of the skew product, so the SE is meaning the skew product. So this basically orbits of my system in the Poincaré space, and I measure this quantity, and I average this to this one. This is basically the same. These are the same things. And I call this the atom exponent. It's some kind of like the average derivative. So I just basically go on orbits, and I just say like I'm expanding, I'm contracting, expanding, contracting, and I'm just taking the rate. So I just take this logarithm, and I just add them. This of course also comes from the fact that if I take the derivative of the composition of these maps, then I get precisely the same kind of thing, because I take the logarithm of the composition, I get the sum of the individual factors. So I take the logarithm so that the composition of maps becomes the sum of exponents. It's important to get the logarithm. As a deterministic system, people also do this. So this is a measure somehow of the average contracting or expansion. So if it's averagely expanding, then we have a so-called positive exponent. That means we have some kind of like e to the something where we grow, and if it's negative, then we have contraction on average. Now we can use the ergodic theorem, and so we take a point, and we do the Laplace exponent, and we express it here in terms of this. If you have this Rooseveldt measure, we can take this expectation. And so we say this is basically a measure of measuring along the orbit, and that it should be equal then to the average over the measure. And that's precisely what we get here. And so we get the expansion of the Laplace exponent in terms of the indirect measure here. Okay, so now it's very interesting that we can show that if rho is equivalent to the back measure on the circle, that then the Laplace exponent will be bounded by 0 from above. So it could be 0, or it's negative. And if it's 0, that's only in this very special case that all the maps deserve the stationary measure for mu almost, psi almost, sorry, this is the measure on the set. That means that for almost all parameter values, this measure is just left invariant. So an example of the last thing, for instance, is if you have a back measure and we just have rotations, everything is just simple rotations, then I can just take lots of rotations. It's clear that nothing will contract ever. We have 0 Lyapunov exponent. But as soon as we put something in there which has some contraction and repulsion or whatever, something that actually doesn't really preserve this measure uniformly, then we get negative Lyapunov exponent. So it actually says basically, unless we take very, very special noise, we have always negative Lyapunov exponent. Good. Yeah. So I'll try to show that. So the idea basically uses the fact that we have a density. The density is lambda is the back measure. So px is the, so it means that the back measure dl, d lambda is then px d lambda is the rho. So then we have a density, we have a function that is the density, And then we basically analyze certain expression and use Jensen in the quality. So let me try to think we have time to do that. It's nice. Exercise. So we have the expression. So we have the expression of the previous page. I'll write it down. Because I'm using quantitative measure. Then we have the output form associated with measure is this form. And then we notice just by that the following line is true. This line is looking further down. So the integral such transformation this follows from the fact that 1 is equal to the measure of a circle. And this can be written as dx. So lambda is the effect measure. And so this says that makes it dx. And then to change, just to change the coordinates. It's just implied. And replace them. Lambda y. Because if you change the coordinates here, then you get an expression that says p y. Very precise difference. Okay, so now we have for 1. And then what we can do is take the logarithm of that. So now, okay, but now if we take the logarithm of this thing, then we use Jensen's inequality. Because logarithm is a complex function. You have the log of integral psi x 0x is larger or equal than integral log of psi x 0x. Maybe psi is not a good function. We'll get one. Let's go back now. Psi. If psi is positively bounded. Okay, if we take the logarithm, then you can take the logarithm there. So we take the formula, this one, let's take the logarithm of that. And of course, then we have the product formula, we can write it out in the following way. So then, logarithm. This is just by using the log of the product of the things is the sum of the logarithms. So I get this inequality, and I just have to observe that this guy, this is the Laplace exponent. And the other guy is okay, so basically this Jensen's inequality is quite elementary. And so this is a property that often pops up in one-dimensional systems. So one-dimensional systems with noise typically have negative data response.
So you integrate the completely by C, and then you obtain the diagonal exponent in observatory.
Sorry, yeah?
So before we get the information on the diagonal exponent, integrate that inequality both sides by measure successful. Of the diagonal exponent of law is integral of the log of the derivative measure log times simple.
this is the average of the. Of the
whatever the measure mean, or so the definition of the viewpoint.
well, some just you have this one, and I think the average. If you put a theorem here, it's also just the average of the stationary measure. Just by the place of the theorem. I don't
in the
need
final line. In the final line.
Yeah, I don't need to.
Oh, but we don't need it.
No. No, I don't need this. No, I don't need that.
But the log of df alpha, so it's integral of log of df alpha, then you pick up one specific alpha, which is not.
Oh, I can of course take the integral of this whole expression over.
Yeah,
I can take the integral of the. I can take from here, and I take then the integral. Sorry, I take this one, and then I take integral over delta.
And you get that.
Okay, so this gives us some idea. So it's quite important to understand that this is a good sign somehow. Right? So we have the random composition of maps, and you think like, why would we have synchronization? It's not a proof, but the fact that we have negative diagonal exponents gives us some indication that on average we seem to be contracting, not to be expanding, which somehow indicates that my stationary measure tends to be concentrated significantly more on the contracting region than on the repelling region, which is not unreasonable to think that in fact, of course, you tend to be closer to more at some place where you contract than where you don't contract. But of course, it's a number game here, so you can't really just argue so simply. But we don't have synchronization then yet. The diagonal exponent is not the eigenvalue of a stationary point or something. It's not a uniform object. It doesn't say that things actually converge. I find that sometimes kind of the people. So the diagonal exponent is the analog of a eigenvalue of an equilibrium point of an equilibrium in an ODE, for instance. At least if you take an ODE, you take an equilibrium point. Say what's the diagonal exponent will precisely be that kind of eigenvalue. But unfortunately, when you go to kind of more general setting, it's not so obvious that the diagonal exponent means the same thing. And so we get actually some kind of bounds or something like that, but they're not uniform. And so you don't really know exactly necessarily what it means. It's an indicator. It's just clear that if you maybe have positive diagonal exponent, you would not expect to converge at all. But it's not so clear that if you have negative exponent, it would. Okay, now this is a classical result here of Lejeune, which is important in the sense that he said that if you have a stationary ergodic measure, and you suppose that the measure is, the diagonal exponent is negative, and I look at this disintegration just at the pullback perspective of this stationary measure, so this integration that gives me information about the dynamics, because it is basically the basis for my invariant measure, which is attracting. This measure is a complex combination of finitely many Dirac measures with equal weights. So U omega is a balanced finite set of Dirac measures. Furthermore, there exist open subsets Bi for each of these AI such that they are mutually disjoint. If you have an all equal measure then the full probability automatically is synchronized to this object. So in the case we saw before, we have basically only one such delta measure. We don't have n of them. We just have one unique attracting fixed point. Jeroen says in principle you can have many, well you can have a finite number only. So maybe it's good to look first at an example.
So what are AIs?
Sorry?
AI omega. What are AI?
A1.
A1 to APN.
These are the this is a random point. This is like my random attractor. It's a random point. So this is the delta measure at AY. So it means that it gives 1 if my set contains A1 of omega. So in the previous case with contractions we had just 1. We had n is 1, just had 1 of them. We showed yesterday that the measure was just like a delta measure.
So that's the general theorem for random co-cycle.
Circle.
What?
Circle.
Oh, circle.
On circle.
On circle.
Circle. Sorry, I'm only on the circle, so I didn't write it again, but it's only on the circle. No, life would be great if it was always true. Unfortunately. Unfortunately, this is just still the simple case. Yeah. So on the circle, and if you have homomorphisms, and I do a random iteration, I have some conditional ergodic measure, I have a conditional ergodic measure sitting on the space, take the delta exponent, then I will have this kind of picture. Okay, so the question now is basically the question like, can you prove this result? And I prepared some notes, but I think it's going a little bit too long to get there. But let me try to tell the story and there's any appetite to discuss more. So the task now is actually, given this fact, how can you now see that there's really synchronization? How can it be like, how can you know there's only one point? Now maybe first, you say like, well, why would it be more than one point? So maybe let's give an example where you know there's more than one point. So it's not a void issue. So suppose we have a circle map. So maybe it's the type we had before, where we have and now make it in such a way that it commutes with the translation, say, over half the circle. As I say here, f alpha. And suppose, for instance, that f alpha of x plus a half is f alpha of x plus a half. Yeah. What does that mean? That means that my dynamics is this transformation x goes x plus a half is a symmetry of this system. That means if I see something happening somewhere, if I shift everything by a half forward, it just happens there as well. Yeah, so that means if I have anywhere a random attractor, a omega, then there must also be an attractor, a omega, plus a half. Right? So then I have at least 2. So, yeah. So definitely there's an issue because it would happen. Good. So that's basically the problem of synchronization, and there's been quite a few papers written about this by various people. But it was a problem that's not really, maybe receives the attention it should, or maybe a very diffuse attention by different people doing different things and not knowing about each other and so on. So it's a bit of a messy situation. But among the people that did something about it was ex-PhD student Julian Newman, and we found later there was actually also a paper by Malishet, but was not published. But Julian gives sufficient conditions which are in most cases also necessary in some sense. So what do we need for the synchronization? We need a unique stationary measure, we need the Laplace exponent, negative, and we need another property is that 2 points are capable of being moved close together. You must make sure that every 2 points, if I start with 2 points in my system, that they have the possibility, the positive probability, to come as close to each other as we like. And so this is and if you have these 3 conditions, then you have such a result of synchronization is that for almost every omega and every point, every pair of points x and y, the distance between those time evolutions eventually goes to 0. Okay, so we have looked at measures, we have looked at this, we haven't really looked so much at this capability of coming close together. So I'd like to spend a few moments saying something about that and how that can be done. So of course one tends to try to prove in some general context that this is true, but the question is how do you approach that? And I think it's a very good example of here where we do dynamics and we don't really do statistics of one-point process. So it's clearly that the synchronization is a very dynamical phenomenon. It cannot be, there's no information in the stationary measure about this. The Laplace exponent gives some hint, but it's a very rough measure. The Laplace exponent is a very rough measure of dynamics. 2-point motions is much more detailed. And so there's actually some elementary result in probability that under some right conditions, which always satisfied in our context, that if we know something about law of 2-point motions, that we can also know about n-point motions where n is larger than 2. The big problem is that for 1-point motions, it doesn't give any information about 2-point motion. That is the object of dynamical systems in a probabilistic setting. At least that's what a probabilist told me, and I completely agree, that it should be the 2-point motion, and not 1-point motion. But actually, most of what we do in dynamical systems on probabilistic methods is an icotic theory, which is basically stationary measures and 1-point motions. And we lose the dynamics in the description. We add things like the Laplace exponent and some other things, but they really give a very rough description only. So how can we do this two-point thing here? And can we understand something about this, the ability to come close together? So let me have to look at, and let's look at this kind of 2-point motion. Well, how do you model a 2-point motion? It looks almost trivial, but it's not trivial. So you take your equation of motion, x goes to whatever it is here, and I just make another copy of the same system, and I just look at them together. Y goes to the same thing. So, naively speaking, you say, well, I'm not learning anything here, I'm just writing 2 times the same equation of motion. What information does it give to me? Well, not really, because I write 2 times the same equations, but I look here at pairs of points. I look at what happened to a pair of points, how they are moved under the same equation of motion. And that doesn't follow trivially from just the one, because it says basically how orbits link together, especially when I do it from a probabilistic point of view. I get different information. So I have a big movie of what it looks like in the, I think just to get some kind of idea of what's going on. And here you see a picture. So here's x, and here's y, and x equals y is the so-called synchronization subspace of this picture. That means like that they have the same behavior. And of course the one-dimensional dynamics also lives precisely on this line. If I just take x equals y, then I just have the one-dimensional picture. I have nothing new. But if I start off the line, then I actually look at what happens to a pair of points. And synchronization means that a pair of points goes to the diagonal. So basically you have a dynamical system, which is that the equations are the same in both, and I'm interested in synchronization. I'm interested whether actually points that start anywhere will converge to the diagonal for some reason. The diagonal is sometimes invariant object. But that's again a dynamical system question. It's a random dynamical system question. Now the question, like, how can we analyze that? So, say for our example. So you see this in the example, you start at a point which is off, somewhere here. Let me see. And then you see it jumps around in this 2-point space, and then suddenly it sits on the back. So that's synchronization. That's really the right picture for synchronization, not 2 points on a circle and see where they coincide. You get a lot of information here. So let me recall the graph, my original graph. This was the F-squared map. And this is the image, the domain, and this was the image. But now I'm actually going to turn this picture into a 2-point picture, where this is x, and this is y, and we're going to use this picture just to know where my fixed points were. Because what happens in this picture, basically for the second iterate, I have stable and unstable points, and in between it's very complete what happens, everything moves to the stable points. It's a very simple dynamics in this picture. So what I do now is I realize that if now this is x and this is y for my 2 coordinates, and I just use the graph as a reminder of how to find the fixed points, then I know that the 2-point system has these 4 fixed points on the diagonal, but it has of course 16 fixed points because it's a cross product of the same system. I have 4 and 4 and 4. I can just combine them in any way I like. And so let me just get rid of this blue graph. Now I have my phase space for the 2-point system. Now another nice thing is that if I sit on such a point here, then once I move here, then my y system sits in fixed point. So these lines are just invariant on the dynamics. Because if my y is in the fixed point system, the fixed point, if I change x, it just changes something here. So these lines are basically stable and unstable spaces for the fixed points in the 2-point system that I have. And what I do is I can write arrows on them and say where you go. So this is a point where you go this way, and here you just find my diagram. And this actually explains, this is like a phase plane analysis like you do in vector fields. And you know everything now about the dynamics. So if I'm in this box, I just converge to this corner. If I'm in this box, I go here, and so on. So what do we see? We see an attractor here, an attracting region with the domain of attraction, which is these regions. And then I have an attracting attractor here, but I also have an attractor here. Here. Here, these two together, and these two together. Okay, so what do we need for synchronization? For synchronization, we need that we can go from anywhere in the plane as close as we like to the diagonal with possible probability. Okay, so how can we achieve it? This was just a deterministic picture. There's no noise in here. So what does noise do? Well, noise comes in the same way in the x variable as in the y variable. So the noise is a perturbation that actually lives on the diagonal, on the vector in the diagonal direction, on the one direction. Now I can play a game. I can say, can I use the noise to get close to the attractor so that the positive probability, so we're close to the diagonal, so the positive probability from any point I'm able to go there. So what is the objective then? To find a noisy path that takes me out of the domain of attraction of things that are not close to the same. If I'm here, then okay, but everything converges here. If I'm here, I'm okay. But if I'm on this guy, then I'm very far from the diagonal. I don't like that. So then I need a perturbation that takes me into another region. So if I'm here, I need to somehow get into this domain. So if my noise is large enough that via diagonal perturbation I can actually end up in such a domain, then I'm clearly okay. The picture is slightly more difficult because I can do this Schuster's set of iterations, maybe not in one step. But take the bizarre example, make enormous noise that up to 1, that I can go anywhere. And of course, clearly I can just jump around and I can, by making perturbations, I can always end up in the right region. So we have to kind of show that this is true. So I have to look at regions which then I get out of the domain of attraction. And so the problem, of course, with my equation of motion was that they both depend on the noise linearly. If I just add the same noise to the points, the two points just translate. So they don't really get any closer to the diagonal by this. You see that the diagonal is parallel to the noise. So in principle, it's not completely obvious, even if I have a noise on the whole circle, that I can go anywhere in one step. Because they can only go on diagonal lines. So we just have to look if we can figure that out. So to get to different regions, so okay, go from this region, for instance, to maybe to this region, and then from this region, I can maybe jump into this region, or to this region, or you must make such a path. And so if it is not so difficult to show here that if the noise is large enough, you can actually find such a path. A slightly more sophisticated analysis should be able to show that indeed you can actually kind of reach this set can apply for the positive probability from such an analysis. And so the two-point motion gives you a much complicated picture. Now, of course, if we have too small noise, then we know already that we can't reach it. So then we sort of stuck here, and we're stuck here and stuck here, and we just can't leave there because the noise is too small, and I have no accessibility to other parts of the phase space, and I can't synchronize. So the theorem of Newman and others says that if there is a problem, so in this kind of system where the noise is basically this interval to diffuse it, as soon as I can find one path that works and I come into an interior, I find nearby parameter values and I get positive probability to arrive in a certain region. Right, so in this case, with some work, you can show for an example, for instance, precisely that this is possible and you should get synchronization. There are more general results of people that say that for circle maps, this is always possible after the certification process when you have full measure. Okay, I think it's time is up, so thanks very much for your attention. And there's some details there that I didn't treat. If anyone's interested, there's some things in this notes, and we also wrote some notes. So if someone's interested, we'll look at some of the details. Thank you.